Well, a very good evening to everybody, and welcome to this very special UEA London lecture being held here at the Royal Society of Medicine. Of course, the lecture today is going to be given shortly by Professor Corinne Quere, and it's in celebration of 50 years of the School of Environmental Sciences. My name's David Richardson, and I'm the Vice-Chancellor at UEA, and I'm really proud to be here this evening to join you in celebrating, or beginning the start of our celebrations for this momentous year for our wonderful School of Environmental Sciences. And I'm delighted to see so many alumni, so many friends of the university here this evening to join us. We're also being joined via live stream. There are many colleagues and friends also in the Thomas Paine Lecture Theatre back at UEA. You're very welcome as well. Some of you might have been to these UEA London lecture events before. Welcome back. For some, it may be the first time. So welcome to you for your first time, and I hope you'll enjoy it so much that you'll join us again in the future. What we tend to do is to have a 45-minute lecture and then 15, 20 minutes or so of questions. The questions this evening will be chaired by Professor Kevin Hiscox, and Kevin is the current head of the School of Environmental Sciences, and also a proud alumnus, ENV79, for those that like to know these things. And then we go for a drink in the foyer, and we can all mingle and talk and share our experiences of UEA, of ENV, and maybe even see whether we can spend some time with Corinne asking yet more questions. So I really do hope that you'll have a wonderful, wonderful evening. And we can also be followed on Twitter as well, #UEA live lecture. So first, the School of Environmental Sciences, 50 years old. And I think it really reflects what UEA has always been about. UEA has been about pioneering the way forward in higher education and research. Its motto was do different, and that's what it's always tried to do. Push back the boundaries, handle education and research in different ways, bringing disciplines together, working together. Coming from a belief that that was the way to actually work on the world's big problems. And there are many, many challenges that the School of Environmental Sciences has worked on very, very effectively over its 50 years. So it was born in 1967, and 1967, if anyone can remember it, was a year where the status quo was challenged. The Beatles famously released Sgt. Pepper's Lonely Hearts Club Band, pushing back the boundaries of music. And in Norwich, the School of Environmental Sciences was being founded, pushing back the boundaries of science and the interdisciplinary collaborations that were going to really epitomise its activities over the subsequent following 50 years. It brought together sciences from many disciplines: natural sciences, physical sciences, social sciences, biological sciences, and they worked together on some major problems. And 50 years later, we can look at the sorts of things they've worked on: understanding global temperature records, the impact of man on climate change, the planet's oceans, how those oceans can act as sinks for man-made CO2 emissions, for example, amongst many, many other great achievements. So great are its achievements that it regularly tops the world rankings for research citations. It's renowned throughout the world, and many, many people, many universities, not just in the UK, but around the world, have copied the School of Environmental Sciences at UEA in setting up their schools of environmental sciences in our image. So it is a wonderful school. It's produced some very wonderful scientists, and we have one with us today, and that's Professor Corinne Quere. She's a professor of climate change, or climate change science and policy, in the School of Environmental Sciences, as we know, but also director of the Tyndall Centre for Climate Research. And Corinne is really one of the world's leading voices in the area of carbon emissions and their impact on climate. She's a trusted advisor, not just to the UK government, but many governments and policymakers around the world on this issue. She's been a contributing author to the 3rd, 4th, and 5th assessments of the Intergovernmental Panel on Climate Change. Her research examines the interactions between climate change and the carbon cycle, including the drivers of human emissions. She's made many advances. She's made advances to understanding the causes of variability and trends in atmospheric carbon dioxide over various timescales, and she's spearheaded the development and the use of carbon cycle models in carbon budgets globally. She's had many, many achievements. She's a highly celebrated scientist, but one of the greatest accolades perhaps came in the last year or so when she was elected as a Fellow of the Royal Society, perhaps the ultimate accolade for any scientist. So it's a great pleasure to be able to introduce her this evening, and Corinne's going to present us with some of the very latest global climate data and examine where we are along the road to complete decarbonisation. Please join me in welcoming Corinne.
Thank you, David, and good evening, everybody. First of all, hello, Norwich. Where is the camera? Here. Hello, Norwich. Hello, Facebook. I think I am possibly the best person to give this lecture tonight on climate change and global decarbonization. But not because I happen to work on climate change and global decarbonization or because of the kind words that David nicely said about me, but because I am 50. And I was born at the same time as the School of Environmental Science. My first exposure to environmental science was at school when I learned at school about wasting water, about the waste, about the pollution, about the chemicals, all these things bad for the environment. So I bring this piece of information home one day, and my mother looks at me very suspiciously. Really, is that what they teach you at school? Have you looked out the window? Water, really? Here is my mother. My mother's family was poor. They were poor because they were a family of blacksmiths. And they fix a horseshoe, a good business when there are lots of horses around, but not such a good business when the horses get transferred and changed into cars. Within the space of less than 20 years, all the blacksmiths lost their job and had to do something else. This is this rapid transition between the horse and the car that you see here in London Street, just across the corner from here, a transformation. So my mother was poor, but from her perspective, there were plenty of resources, including water resources. That changed very rapidly. You see now, moving forward a little bit more, in 1950, the smog that were in the street of London at the time, black smog poisoning people's health, making everything look gray, a little bit like you see in the news for BG nowadays. There was already quite a lot known before the School of Environmental Sciences about climate and climate change. The greenhouse effect had been discovered theoretically 200 years ago by the Frenchman Joseph Fourier. It was followed by laboratory demonstration of the absorption of heat by greenhouse gases by the American Eunice Foote, and then by the Irishman John Tyndall, which gave his name to my center. We borrowed the name from him more truthfully, and followed then by the very first estimate of increasing greenhouse gases would affect surface temperature by the Swedish Svante Arrhenius over 120 years ago. It is with the book of Rachel Carson, Silent Spring, that the extensive effect of human activities on the environment began to be taken seriously and recognized seriously. So it is during this troubled period that the School of Environmental Sciences and myself came to be. And shortly afterwards, in 1971, the Climatic Research Unit came to be, and much later, in 2000, the Tyndall Center for Climate Change Research. The late 1950s is also the time when direct observations of atmospheric CO2 concentration began at Mauna Loa Station in Hawaii. This is what you see, the dark dots here, which eventually have been brought, the measurements, the estimates have been brought backwards in time through the help of ice core data. But the direct measurements here that we had for a few years at the start of, at that time, showed already an increase of atmospheric CO2 to 320 parts per million, that's ppm here, an increase of about 40 parts per million compared to pre-industrial level. And this increase was aligned with the beginning of very large rises, major increases in carbon emissions from burning of fossil fuel. We had no temperature records at that time globally, but if we had had record, this is what we would have looked like. Warming of about 2 degrees Celsius only. The presence of natural variability in the temperature record was already recognized already then. And in fact, a paper published in 1981 by colleagues in the School of Environmental Science at UEA said that although it is widely believed that increasing atmospheric CO2 level will cause noticeable global warming, at that time, the effects are not yet detectable, possibly because of the noise of natural climate variability. The estimates of long-time record of surface temperature started with the development of objective techniques at the Climatic Research Unit with the first paper, which you see here, on Northern Hemisphere land temperature, published in 1982, and following on from this global temperatures on land with contributions then of the ocean temperature in 1986, establishing the long-term collaboration between the University of East Anglia School of Environmental Science and the Hadley Center that continues to this day. Let me fast forward to now. My daughter was born in 1995. One thing that marks time of this period is the emergence of the digital world. It was still on the margins. If some of you, if you were there, 1995, you will remember, you might remember that it was still in the margins, but it emerged about that time. And I have learned a good lesson myself about changing perspectives at the time my daughter was born. So here's the story. Here I am, working in East Germany. There is a guy there, the head of IT department. I don't know about you, but I don't ever speak to IT people. They have the power, all the power. They have no name. They're all called IT.helpdesk, no name. But this guy, the head of the IT department in East Germany, I have to talk to him. I have to talk to him once a year because we are born on the same day. He's also 50. So one day, 1 year, so on D-Day every year, unconsciously, we look for each other in the corridor. So one day I see him coming. So I approach and go, "Congratulations, Bertram." And he comes to me, "Congratulations, Corinne." That's what they say in East Germany. I think it's "Congratulations for still being alive." But I haven't tested this. But anyway, 1 year I say, "What's up since last year?" Obviously, because I haven't spoken to him in between. So 1 year he says, "Fabulous progress. Wireless is coming to our institute. Wireless, you can read email in the corridor." This is progress, I think. Are you sure? Progress? Yes. And so I say, or think, I don't know, who cares? See you next year. That was it. Typical IT conversation. So all this to say that I totally missed it. The wireless, I did not see coming the rise of the digital area. It passed me for 2 decades before I grasped its importance, before I grasped its usefulness, before I have this thought that it's inseparable, I play with all the time. I was born in the area of environmental pollution. My mother was born in an area or in a world full of resources, and now my daughter is born in the digital world. This changes perspective radically. And by the way, I think I have the less of all the worlds here with the polluted environment. But here we are, 50 years later, to come back to the data here, emissions tripled here, 36 billion tons of CO2 from fossil fuel alone. The rise of CO2 in the atmosphere crossed 400 parts per million level without the blink of an eye, and the world temperatures have now warmed by a full degree centigrade. By the way, do you understand these plots here? That's time here. No axis, you just have to look up the number. They're here. I'm just trying to simplify. Okay, now is a good time to examine the temperature record. So we have 150, 70 years of temperature record here. I have to say, though, before I give you all the science here, that we do get a bit creepy in science sometimes. We had this pause in warming temperatures recently. It's here, the pause, the hiatus. Have you heard about that? Yeah, in the newspapers, they liked it. In the newspaper, they were drooling over the hiatus. It was tough. It was tough for us. It was a constant challenge explaining the global explaining why the global temperature had barely risen, explaining the role of natural variability in this, and saying something like, "Don't worry, it will warm again," something like that. So when finally, and it was hard. I have to say it was hard. Do you remember? And so when eventually in 2015, when the world temperature, so this first of the high dots here, eventually in 2015, when the world temperature smashed the record, I went, yes! And then in 2016, yes! And then again, the Metal Fist this year published their forecast for 2017, and it's going to be warm again. And I have to say, I was also a little bit happy that year. I'm not proud. I'm not proud of this. This is a complex situation. It's on the one hand, it's a very exciting field of research, the science on climate change. It's incredible to have this changing environment in front of your eyes. But on the other hand, it's also an absolute dread about what it actually means. So given all the current knowledge, there are two things that I want to firmly say about this record, which actually you probably have read already. One is the left-hand side, which is warming of the climate system is unequivocal. So the climate system here, we're talking about the planet, the surface of the planet, essentially. And the other one is that warming of the climate system from human activities is also unequivocal. And now to make sure that there is absolutely no misunderstanding between you and I, and also Facebook and I, and UEA and I, Norwich. Hello. Unequivocal means leaving no doubt, unambiguous. And so let me find my notes here so I say what I have to say. Okay. I'm going to provide four key reasons on both sides. One, I'm starting to the left. That's usual, left to right. One, the warming is widespread. So it is not regional warming, which would distinguish it from natural variability. It is more heat on the planet. There are independent measurements of the large-scale warming from land, from ocean stations, ship-based observations, satellite data. 2 and 3, it's the effect on the hydrosphere. So the sea level is rising, again, from independent tide gauge observations and satellite data. I put the satellite data here in red from NASA. And it's probably caused by warming waters expanding, and they can only expand upwards, so it's causing the sea level to rise. 3, snow and ice are melting on a large scale across the world, with the Arctic sea ice, which you see here, having lost almost 40% of its area within decades, literally collapsing here, also seen from satellite. And the latest evidence, which is truly amazing, I mean, it's more complex, I'm sorry, but it's fascinating, and that is the acceleration of the water cycle, which you see in surface salinity. So this here, the colors, are trends in surface salinity. So red is when you have a concentration of salt in the water, and blue is when you have a dilution of salt in the water. And so these are the trends, the changes over 50 years. And what is overlaid there, the lines, are the contours of the mean salinity. So the trends in salinity and the mean salinity match each other, and that means that you have an acceleration, actually, of the water cycle. I mean, this is a beautiful piece of science. Let me now go to the right-hand side. The 4 reasons why the warming of human activity is also unequivocal. Here are the 4. Number 1, we understand the processes. As I mentioned earlier, this is not new science, this is not new physics. The scientific understanding is heavily scrutinized and challenged, and it is robust. It's physics, it's robust physics. Number 2, that's the weakest. The observed rate of warming, which you see in blue here, is more rapid than any centuries in the recent records, which you see in the long tail here of 1,050 years. And that evidence is strengthening with time as the temperatures continue to rise, obviously. 3 is the most powerful because it's the combination of 1 and 2, essentially. It is the challenge of reproducing global temperatures, which you see here, happens to end with the pause here, that's what you see. Is the most powerful, the combination of 1 and 2, the challenge of reproducing global temperatures changes in models. So you have a hypothesis in science, you test it. And the way we test hypothesis when we cannot do experiments in laboratory, like with the Earth, is to put the physical equations in models. And, so where am I? So there we go. So these are all models. So every single line here is different model realizations. There's about 20 global climate modeling groups around the world. And when these models only see changes in solar activity and changes in volcanic activity, which actually, by the way, we observe and keep track of, so we know when the patterns change and so on. So when you force models, so when you let models only see the natural variability, this is what they do. So they go straight, they have wiggles. These are all volcanic eruptions here that you see. There are trends in solar variability here. And it is only when you put emissions, so greenhouse gas emissions and aerosol on top, that are considered that the models can reproduce the observed trend. There we go. So this is without greenhouse gases, and this is with greenhouse gases. This is very, very strong evidence here. And you see there's not one single model that does, oops, sorry, don't read. There's not one single model that actually reproduces the trend in observation. Not one single model. Blah. The last one is my favorite. There is no alternative explanation. This is how science works. Explain the observations, please. You think that it is something else? Fine. Show me the equations. Put this in a model. Make your proof. Untested hypotheses are just not good enough. The warming that you see here is enormous on planetary scale. It means that the entire environment and its functioning is not stable. This includes environmental conditions that support water availability, conditions that influence weather, food production, forest fires, fish stocks, and that favor or not pest and disease outbreak. In the latest analysis of extreme events in 2015, without exception, human-induced climate change made the heat-related events either more frequent or more intense, or both. In the UK, heavy rainfall and sea level rise and associated risks of flood are the largest known, thought to be the largest major threat to community, businesses, and infrastructure. The unstable climate that we are causing, that we are living in, matters because the planet has a growing population of 7.5 billion people to feed and maintain in relative stability, and changing environmental conditions provide actually triggers for instability, both climatic instability, physical instability, and social instability. The threat to global stability is widely recognized from climate change, and that takes me to the interface between science and society. There is no other area of science where this interface is so carefully managed. The Intergovernmental Panel on Climate Change, the IPCC, but not the Independent Police Complaints Commission, is the mother of all scientific assessments. Established in 1988, it has provided substantial assessment, which are here, 5 assessments here, of the evidence of climate change, producing over 4,000 pages of supporting evidence over 5 major reports. Because my boss is here, I feel obliged now to brag about the UEA contribution to the IPCC, which I think is here. UEA is the university that has made the most substantial and sustained contributions to IPCC across disciplines. Thank you. Thank you very much. Thank you. With 50 chapter authors across five scientific assessments. You see Tim Osborne here, who is also here. Tim Osborne and myself. Here, Tim from the Climatic Research Unit at the last government approval session of the IPCC. Now, my husband thinks that I work late in the evening, but look at what I do when he's not around. This is 4 a.m. It is really 4 a.m. You remember? That's for Tim. He remembers, obviously. Of course, you remember these things. The extent and quality of the international effort of the IPCC has earned IPCC the Nobel Peace Prize in 2007, and that's for the science. Let's move on to the policy. So the policy people are much more civilized. First, they work during the day, 4 p.m. They also produce a number of pages that are scientifically robust and understandable. On the content of this report, so this is the Paris Agreement on Climate Change that was approved at this session here, thanks to the lovely people that are here, particularly the two ladies on the left. So this is the actual Paris Agreement on Climate Change. You can read it; it's readable. There are two sentences that are particularly relevant to today's presentation. One is the ambition of the Paris Agreement is to hold the warming to well below 2 degrees Celsius and pursue efforts to limit warming to 1.5 degrees. And the second, which made working through the night actually worth it, because I think it influenced this second session, which is to reach global peaking of greenhouse gases as soon as possible. I have to say this bit is a little flaky, but with rapid reductions thereafter, that's obvious. But in order to achieve a balance of anthropogenic greenhouse gas emissions and sinks. Before I move to the future, I will come back to this in a minute, don't worry. Before I move to the future, I want to say a few words about the carbon cycle, which is my core research area. This graph here I've showed before. It shows the CO2 emissions, which is a rate here per year, change per year, and the CO2 concentration in the atmosphere. So the emissions here we estimate from energy data, but CO2 concentration we actually measure. I mean, Andrew Manning, who is here, that's his core research area. Only about 45% of those emissions that we put in the atmosphere remain there in the atmosphere, and that is because of the presence of large carbon sinks. So the natural environment absorbs 55% of the emissions on average, so that is the land and the ocean. And therefore, the sinks introduce a mismatch between the growth in emissions, which you see here, and the growth in concentrations, which you see there. Now you have, if you look carefully here, you see with your eyes there that the last 3 years of data the emissions appear to be flattening out. Whereas if you actually have bionic eyes, you might see that the last dot here really sticks out. So the growth in emissions in 2016, the growth in concentration in 2016, this was extremely high, while the emissions did not grow at all. And so that created a little bit of confusion. If you paid attention in the media, last year, around October, November, within 3 weeks of each other, 2 articles came out. One said CO2 levels mark new area in the world changing climate, which they did. And one said global carbon growth stalls as the US coal continues to slump, which they did. And so that's pretty confusing. And so I was challenged to explain these data by Jeff Tollefson, who is the news editor at Nature Journal. And he sent me an email. So this is a tweet here. It's not an email, it's a tweet. But he actually wrote this text in an email. Innocently, I get this by email. I don't know that he's tweeted this thing. So I just read an email. He says, emissions are flat, CO2 is skyrocketing. When will we see the signal? So when will we see the emissions are stalling? When will we see the change in emissions in the CO2 concentration? So there I am doing my own work, blah, 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 don't know, distracted by something. Reading this email, I answer straight away, oh, about 5 years. And then he sends this email to somebody else. And this other person did the same thing as me, was distracted by his answer straight away, oh, about 1,000 years. And then, and then it came out via Twitter. My email came out via Twitter, and the other email, immediately the both of them. So I thought, actually, we'd better find out what's happening in the reality. So both answers were immediately tweeted, and so I spent the last few months to try to actually resolve this issue about how long will it take before we can measure a change in emission, which is deduced or estimated from energy data, into a change in concentration. So, so what did I do? Oh yes, okay. So what I did is I relied on the Global Carbon Budget Annual Update, which is a fantastic exercise of the Carbon Cycle Research Community, of which there are many members here. And so what we do there every year since 12 years, under the umbrella of the Global Carbon Project, what we do is we amass data and estimates of the 5 components of the global carbon cycle: 2 emissions, fossil fuel deforestation, and 3 sinks: the atmosphere, the land, and the ocean. We amass a large number of data. I mean, there's 100 contributions here, individual contributions. We amass them, we sum them up. If we had a perfect understanding of the carbon cycle, this red graph here would be 0 all the time. It would be flat. And with this, we could say straight away, we could see straight away the change in emissions in the change in atmospheric concentration, because we could explain the variability. Now, you will see that it's not 0 all the time. It is 0 on average, though, and there is no trend, so that's already pretty good. But there are big areas of uncertainty. It's not uncertainty here. Actually, we call it unaccounted carbon. So this is either areas where the emissions have been over or underestimated, or more likely where the carbon sinks are responding to climate variability in ways that we do not yet understand and that are not included in our model. So I'm doing a little analysis here of exactly how long it would take at the moment to be able to detect an emission change in concentration. The answer is going to be about 10 years. That's actually the frontier of research in my field, but unfortunately, my grant was just rejected yesterday, so it's going to take a little time to find out. That's life, by the way. It happens all the time. Okay, back here. Now, let's have a little glimpse into the future. The warming from greenhouse gases is, sadly enough, not reversible on kind of human timescale, at least not for many centuries. So the temperatures will remain elevated in the foreseeable future. What you have now is what you get. Whatever we do, foreseeable future, to whatever level we let the temperature rise, and a substantial amount of adaptation is going to be needed to the new climate, no matter what, particularly as the sea level rise will continue to rise even after the temperature have stabilized until the new cryosphere, so the snow and water and temperature, reaches a new equilibrium, and the temperature of the oceans. There is only one way, I'm sad to say, to stop the rise in temperature for any level of warming, and that is to bring down the carbon emissions to 0 or very nearly 0. Whatever the warming, whatever the level, eventually the emissions have to come down to 0 or very nearly 0. The model projections that limit climate change to well below 0 look like the green one here. Where the emissions decrease as rapidly as they have increased, at the same rate as they have increased globally, with the need for negative emissions, that is taking CO2 out of the atmosphere and putting it underground, sometime in the middle of the century. The exact level of these emissions is not known precisely, but the more we wait to decrease emissions, the bigger the need for negative emissions later on, or the higher the temperatures. Now, whether emissions, negative emissions, whether these negative emissions here are possible or not, and at what cost and what efforts and who pays and what the financial system is huge research area and huge policy discussion as well. Let me talk about uncertainty. Now, I said some pretty affirmative things about climate change before. I haven't talked about uncertainty yet. There are uncertainty, obviously, we know this. The uncertainties are mostly on size. They're on how much warming are we going to have for a given amount of CO2. This is the bulk of the uncertainty and the discussion and the arguments that we have in the field right now. It's a super important question because here I show what is the uncertainty and the projection associated with this scenario of future emissions. The risk, if the real world happens to be here, if the projections, if we were able to follow this pathway, the risks is much smaller than if the real world happens to be here. At the moment, you have to handle this uncertainty from a decision-making basis. We don't need to delay global carbon emissions very long to exceed the 2-degree limit. This brown scenario here, where peak emissions is delayed by 20 years, that's not very much, rises atmospheric CO2 by another 150 parts per million, and temperature by almost 1 full degree, not quite, 0.8 degrees here, compared to the green scenario, thus tremendously increasing the risks of negative and widespread impacts on society and instability. To deliver even the brown scenario at this point requires enhanced effort and concerted actions. Many of my colleagues think that the green scenario is impossible. Let's have a look at what is happening now in this little elbow here so that you can form your own opinion about what is possible and what not, and perhaps also about what you're prepared to do yourself. Here are the 4 biggest emitters. In China, coal use here is decreasing recently since 2013, leading to a flattening of their emissions and possibly a small decrease. In the US, emissions have been decreasing since 2007 here, and in Europe since 1980 here. But in India and other developing countries, emissions are on the rise. I'm going to dig into this. This is the most difficult slide. Okay, I'll run you through it. It's difficult, but you can do it. We use decomposition to understand the underlying process. It's also the most interesting, I have to say. Well, maybe not the most, but it's very interesting. We use decomposition. So this is a Kaya identity decomposition. The drivers behind the CO2 emissions are thought to be GDP, which is wealth, a measure of wealth. The energy intensity of GDP in purple here. So is GDP made of activities that require a lot of energy, essentially? And the carbon intensity of energy, which is this orange here. So is energy from fossil fuels or from renewable? This is what these show. Blah, blah. So all the plots that I will show now are smoothed over 10 years. They have been done by my colleagues, Glenn Peters, and published in this publication here. So let me show China first. So for China, this is here, the black line is the growth in emissions. So emissions in China were growing, this is percent per year, very, very rapidly in the 2000s and less so. And now the growth was approximately 0 in the past few years. So the things that are at the top here are pushing growth in CO2 emissions, and the things that are at the bottom are reducing the growth in CO2 emissions. So in China, you see that GDP was very, very important in driving their emissions. I mean, this is expected and normal, very high GDP, and that what they call rebalancing the economy with their GDP actually rising by only 5% per year is really one of the main causes behind the changes in China. There was also, though, changes in, this is efficiency improvement in energy of GDP. And this orange line here is particularly interesting because this is the signalization of decarbonization of the energy. Now, we think of China as lots of renewable and so on. There's a big narrative around this in China. So I'm going to explode this orange bar here into a green and another orange bar. And the orange bar here is the share of fossil fuel, which is essentially having more renewable energy in the fuel mix. And you see that this is very important, but it's also equally important in China that they have decreased their coal consumption while increasing oil and gas consumption, so rebalancing their fuel mix. We can even push this a little bit further and show that now the growth in exajoules per year, so an energy unit, this is all about energy here, that the growth in recent year in the energy use in China was not based on fossil fuels as it was earlier, but it was rather based largely, by and large, on renewable energy. This is extremely good sign, but the amplitudes here are still quite small. In China, the other renewables is mostly hydropower, actually, and a little bit on nuclear. Yeah. Okay, the left figure, let me go back to the left figure here. So now we want to think a little bit together about what's going to happen in China in the next few years. Because China is the biggest emitter worldwide, what happens in China is extremely important. That at the moment drives global emissions. So let's think a little bit about what's going to happen to the growth in emissions in China in the next few years here. Now the GDP, for this black line here to decrease below zero, which would mean emissions would actually go down, either GDP would need to decrease further, which is actually probably unlikely at 5% per year for a big country still developing like China, or the energy intensity or carbon intensity, so the two bottom line here, the black line, would need to improve faster. At the moment, these two blocks here are aligned with China's 5-year plan, so their own planification, economic planification. So probably the most likely outcome for China in the future is more or less flat emissions. Unlikely back to their growth of the 1990s, but also unlikely decreasing rapidly. But who knows? We miss the growth, we miss the decrease, we might miss what's happening again. Here's the story for the US. The drop in GDP from the global financial crisis, these are 10 years running mean here, is clearly visible, as is the recovery from the global financial crisis. But the decrease in emissions in the US is largely driven by this green bar here, which is the move from coal to gas, shale gas in the US, I'm afraid, mainly with growing renewables, mainly solar and wind, but not systematically so, as you can see here on the right-hand plot. Here is the story for the UK. Again, the global financial crisis and its recovery, both clearly recoverable, recognizable, with consistent increase in the share of renewable energy, particularly seen on the right-hand panel here. This is renewable energy actually replacing fossil fuel energy, as you can see here, fossil fuel energy being replaced by renewable energy. So different countries, different circumstances. There is nothing, in my opinion, in those plots that suggests that decarbonization in the future will happen naturally. The continuation of these trends of decarbonization requires constant renewal of efforts in various sectors, which reduces price and increases uptake worldwide. Let's hone in on the UK for a bit, because it's close to our house here in London and Norwich and Facebook. We take a look at a few sectors in the UK. Selected sectors, 75% of the emissions, because I want to explain things here. Most of the reductions in emissions in the UK come from the power sector, where coal is being phased out here as in the last few years. There is a gentle decrease in emissions in building, but this is threatened now that the investment in insulation have basically ceased. No change in transport in recent years, incredible. Barely any changes in agriculture and land use. For the moment, we are surfing, our decarbonization is surfing on decarbonization of the power sector, replaced by renewable in large part, but that's not going to last. The UK Climate Change Act stipulates that emissions need to decrease 80% compared to 1990 level by 2050, so that's here. And to be on target, much broader decarbonizations need to take place across all sectors as a rising, across all sectors. So for 2030, there are obvious gains to be made by stopping waste, reducing, improving efficiency, for example, across the sectors. This has to be harvested, but there are also opportunities come from the drop in battery price and the drop of cost of electric vehicles, and that needs to start to spread so much that in 2030, and that is not very far away, it's possibly your next vehicle or maybe the one right after that, new cars and vans should be largely electric. Similarly, low carbon heating around that time, 2030, not far in the future, should begin to be widespread with all gains, as I said, harvested elsewhere. It's not enough to look at 2030 though, because we also need to think about the so-called difficult to reduce emission, and that is agriculture, aviation and shipping, and land use strain, and some industrial processes. We have done a lot of work at the Tyndall Center on aviation and shipping, showing that there are in the shipping industry a lot of opportunities, but in aviation the technological advances are much more difficult, and at the moment the foreseen improvements in the technology just offset the anticipated growth in flying. For this reason, at the Tyndall Center, we have put a lot of thinking into the development of research practices that reduce the need to fly to meetings, particularly reduce long-haul flights, which are particularly damaging, which is detailed in this working paper that you see here, accessible on the internet, also for the Facebook people. It's also almost certain that it will not be possible to decrease all greenhouse gas emissions to zero, and therefore we need to plan to remove CO2 artificially from the atmosphere through carbon capture and storing it underground, and that needs development, it needs financial mechanisms to pay for that, and so on. So that's for the UK. Before I close, I would like to say a few words about the risks and opportunities. I mean, this is a very interesting political environment time here. It's not just the digital that is changing, there's more to it. On the risks, climate change is not a political agenda. It is an agenda about well-being, about peace, about stability, and about managing the risks we face in our society. This management of the risks can be done by people on the left or on the right of the political spectrum. It is an agenda for the long term for people and society with visions. Second, fragmentation of global politics, so fragmentation, is the biggest challenge in addressing climate change now. It is a miracle, I tell you, that we have the Paris Agreement on climate change, but its implementation requires concerted action. If one country pulls out, that's hard. If then another one follows, and another one, and another one, it does not work. The delays become unacceptable, unbearable, the risks rise very, very rapidly. Brexit negotiations need to think about the environment, and new environment policies are needed regardless of Brexit, and so let's not forget this. On the opportunities, two stand out particularly. One is the improvement of air quality from moving away from fossil fuel. We accept levels of pollutions that are so incredibly high that I have to hold my breath when I sit in traffic on my bicycle. If you cycle, you know exactly what I mean. The numbers of avoidable deaths are astronomical, especially in children. The other opportunity regards businesses and jobs, provided that we can manage this in a way that those who will lose from decarbonization, just like my mother's family lost when we moved from the horse to the car. So provided that we can do that, an incredible low carbon economy market is emerging now. It is already employing possibly as much as 500,000 people in the UK, with a turnover in the tens of billion and possibly even more. It is projected to increase by more than 10% per year in the next decade. This market, as is the market for digital, are exploding now, and I hope that they will trigger the acceleration in the decarbonization that is needed worldwide. To finish, this is my last slide, just to say a thought that it is not necessary to see the entire path before taking it. It is enough to see the end point and to see the start, and options will come from moving forward. Thank you very much.
Well, thank you, Corinne. That was quite an exposition of the current challenges that we face as a society globally, and entertaining too, so thank you very much. We have several audiences that may wish to ask some questions now. I might take, depending on how many there are, 2 or 3 at one go, so if you'd like to put your hands up now, happy to field some questions from the audience. And they're all stunned, Corinne. Over here. Thank you.
Thanks very much for a very interesting talk. Can you say anything about the processes by which we might extract CO2 from the atmosphere once it's already there?
Are you going to take more? I start with this one. Okay, processes. So the one that is possibly the most promising is bioenergy with carbon capture and storage. So you grow crops, essentially you harvest them, use them for energy, and then you capture through chemical processes the carbon and store it on the ground. There's also actually a lot of, there's several methods being explored, but there's also one that is, I would not say promising at the moment, but if it worked, it would be fantastic. It's called direct air capture. So taking CO2 through chemical processes that you can then recycle, but the costs at the moment are extremely high, and whether that can be implemented on the large scale is just not convincing at the moment.
Okay. There are a couple of people here, or 3 people actually. Perhaps we'll hear their questions at the front. We need to use the microphone so that our remote stream can hear the questions. Yes, sir.
Hello. What was the reason for the warming poles at the beginning of the century?
Okay, and then a couple more in the same area. Yes, yeah, please answer your question.
Well, my question was about methane and the move towards the sort of lighter molecule, towards the methane molecule. Is that a good thing? Because I read a very scary story today about the Chinese actually mining methane hydrates off of the seabed off the coast of China. And apparently they've done that successfully for the first time. Now, you know, from my perspective, methane hydrates create mass extinctions. It's a very, very scary prospect of actually being able to mine that sort of material. But is the move to a lighter molecule better than keep on producing more oil and consuming more coal?
Okay, and to your left, the lady 3 seats to your left.
Hello, I don't know if this is an appropriate question for you or not, but I was just wondering about the apparent good news in the UK about the decline in carbon emissions in terms of energy. But I don't understand, I mean, I understand that we're not really investing in true alternatives on any, relevant scale. So is it likely to become bad news in the future because we haven't properly invested in ongoing alternatives?
Okay, I have
Three
a go
more.
now.
Yeah.
On the warming, you asked the question. On the warming pause, so it's not one single answer. So there's at least three elements of it. One is incomplete observation. So we did not have data in the Arctic. So the Climatic Research Unit data has gap in the Arctic where there was particularly lots of warming that was not captured with the data. One is that there has been smaller but multiple volcanoes in this decade that cool the climate a little bit. I mean, we're not talking about big effects here. And one is natural variability in the ocean in particular that has brought sort of heating from the surface to the deep ocean, which makes the ocean as a whole warm, but not the surface ocean. There's an excellent summary of this just published last week in I believe, in Nature. On the methane, I mean, more fossil fuel is more fossil fuel in the atmosphere, right? There are large stores of methane hydrate, so if they are to be exploited, then it's more warming. I mean, methane lifetime is shorter than CO2 is 10 years, around 10 years, whereas CO2 is 120 years. So methane will naturally be removed from the atmosphere. On the other hand, it's a more potent greenhouse gas. So it's not a good alternative, I would have said. Investing at on the CO2, yes, that exactly. I mean, at the moment we're surfing on decarbonization of power, but you can only go so far. We're almost there at as much as we can do, not quite, but almost. And so we need to invest. We need to have policies and efforts that do these standards, for example, in construction. Why are we still constructing houses that have inappropriate insulation and that don't have solar power? In car regulations, we need to be investing in how do you say, recharging facilities for electric vehicles, so people have confidence. You don't have the anxiety range that people have with electric vehicles at the moment. We need to make these investments. When these investments are made, you see that they have effects afterwards. We need much, much broader investment, not just in the power sector, which they have been good, and it's good to have decarbonized power sector to feed all these other sources, but it needs to be very broad.
Okay, now we have a couple of questions out there in the ether, I believe, Holly.
We do. We've got two. We've got two questions from Norwich. So would you like them both now?
Yes, please.
Great. So firstly, you spoke about the importance of China in reducing emissions of carbon, but could you comment on the role that we in the developed world play in exporting our carbon emissions by relying on products from China? And secondly, what about the role of nuclear? Is that the only way forward?
Should I take those?
Yes,
Excellent questions. Thank you, Norwich. China, yes, very good. So this is a big issue because emissions are calculated based on what is produced in the territory. And naturally, in this country, for example, in the 1990s, a lot of the industry went to China. And so we have gained we have gained from reductions in emission in the industry because of this, but it's not really satisfactorily gained, really. And then as a result of these changes in the economy that was before climate policy, nothing to do with climate policy, as a result of this, we now buy stuff from China, and that carbon that is embedded in that stuff, anything here, this, for example, embedded in that stuff is accounted in China. It was so bad that between, let me get the numbers right here, between 1990 and about 2005, the emissions in the UK, territorial emissions, were decreasing like this at that slope. And if you accounted for the emissions that were accounted elsewhere, then we had a growth, an actual growth in emissions until about 2005. But that's no longer true, actually. If you look at the latest data over the last decades, both the emissions at the territorial level and the consumption emissions are decreasing. So at the moment, in the last 10 years, we have real decarbonization of the economy. It would be very good if we started accounting for emissions on a consumption basis, but there are issues with the data. I mean, there are already issues with the data territorially, but there are issues. Actually, I should look at the camera here rather than at the speaker. And consumption is more difficult. The other one was the role of nuclear. The role of nuclear. Look, we have to change from fossil fuel emissions into another source of energy. There is a little bit of leeway for preferences here. If a country wants or wants not nuclear, then you can actually make actions to have the fuel mix that you want. It's easier, of course, if we accept all forms of renewable energy. So if we accept nuclear and we accept wind and solar power and whatever works for us, if we have a mix of technologies, that's also best because it provides more flexibility. Nuclear has a lot of advantages. It has a base load that is very constant, and you can make investment on the long time. On the other hand, there are lots of negative sides of nuclear. So there are alternatives to nuclear, but if you want the alternative, you have to make the investments elsewhere.
Okay, a few more hands going up. Yes, one just to hit the front and one towards the back.
Is deforestation as big as a factor as burning coal in climate change? And also because you said you're trying to capture carbon from the atmosphere, isn't it easier to keep the greenhouse gases inside the ground, like because of the warming of the tundra in Siberia, the methane gases are releasing in the atmosphere, and that's a more powerful greenhouse gases than carbon dioxide. Is that easier to hold them into the ground and try to get them back in there?
Okay, thank you. And just behind you, there's a question, actually, if you wouldn't mind.
And exactly what are the risks of global warming? Are the risks towards the humans or for the planet?
Thank you. Just behind you there. Thank you.
You mentioned the idea of bioenergy crops linked with carbon capture and storage. Are you sure about that? Because I work in agriculture, we're very concerned about global food security. So any land that's grown for those crops, you're not growing food on them. So there's a conflict there.
And a question just at the back as well here. Well, a hand went up, I think. Thank you.
Yes. One. Oh, hello. I was wondering if you hear about deforestation. I was wondering if the answer to problems with carbon dioxide in the atmosphere increasing would be to increase the amount of planting of forests and things like that.
Okay, some related points there.
Can you repeat the last question? Have you understood the last question?
But the value of planting crops to sequester carbon.
Yes, thanks. A lot on deforestation. So I haven't talked about deforestation today, but it's really important. In CO2 only, deforestation is about 10% of the emissions of CO2, but if you account for full greenhouse gases, it's much larger, about 25%. So it is a big factor. It's a factor that is difficult to manage because we deforest for a reason. We deforest for economic reason. We deforest to grow food. We deforest when the soils become too poor and you need to go somewhere else. And so in the terrestrial area, it's quite difficult to decarbonize agriculture. It's not so difficult to control deforestation, but you have to see it in the bigger context of the value that it provides. You had some. I'll skip the methane hydrates. I liked your question about exactly what are the risks to global warming. I mean, I wish I could answer this exactly, but exactly I cannot. But I can say that the risks are widespread.
But humans as a species, we're doing better than ever. Are the risks for the planet or for humans as a species? Because the planet had increases in carbon dioxide in its history, we had peaks, not in recent history like you mentioned, but on the history of the planet, we had peaks like that even.
Yeah, I mean, we had, yes, the environment has a lot of instability.
Can handle it, and the humans
the planet is going to respond whatever happens. So the planet is going to rebalance, the ecosystem is going to rebalance to a new temperature. There are things that can happen. For example, ocean deoxygenation is has happened recursively in the geological past. I mean, it depends what you value in terms of the stability of the environment. I think the risks to society are actually very severe. Yes, we are better off in our society than ever, but we've had wars before, we've had tragedies before, and maintaining this political stability depends on the feeling of justice and on the feelings of fairness of international relationships as much as on the exploitations of our resources. What we are doing with accepting higher levels of climate and having an unstable climate is increasing the risks of instability, the risks that the food that we produce is not right or fails in some years in places where people are particularly poor, and a range of risks that will require adaptation. I cannot say exactly, though. Let's move on to the crops, because that's also a very good question. Who asked this? Crops. Crops. Am I sure about this? Not at all. I mean, this is one of the biggest questions, is can we actually do this with bioenergy, with carbon capture and storage? You're completely right about the competition with global food security. We have more people eat more meat, which is, I mean, it's good that they eat more meat, I don't know, but more is good. And there's competition both on the location, on the resources, but also indirectly via price. So these are all extremely important questions, and in fact, we have just got a grant in the Tyndall Center to examine these questions here. And the last one was about the value of...
Well, similarly,
deforestation, planting crops.
Okay, we have just a question, I think, from
Hi,
Norwich.
We've actually got a question from India, I think, which has come in via Facebook. And we might have to make this next one the last one, because we've only got 10 minutes left of life on the live stream laptop, unfortunately. Technology is going to fail us. So the question from India. In India, recently, we have had a policy push on solar, with solar unit prices falling rapidly. What are your predictions on India? And do you think with access to this kind of technology, India could leapfrog other countries?
And then there's one question at the front. Here's the last question.
It's quite a broad question. I don't know how easy it'll be to answer. But in light of the task we face as a global community to decarbonise in the years ahead, where do you think the push needs to come from to make that change actually happen? Is it from a political... you said that it's not necessarily a political issue, but obviously with things like the Paris Climate Agreement, it's essential to moving forward. Do you think it needs to be a big change from industry on a sociological level? Where do you think the push really needs to be for it to be effective?
Question?
Thank you, India. In the Carbon Cycle Research Community, we are all eyes on India, because what happens in India is extremely fascinating, for one thing. Very, very rapid growth, very rapid demand on energy. India is extremely poor, so the way India develops will be crucial, I'm sorry to say, for the levels of climate change that will happen. There has been large investment in solar power, and one of the biggest good piece of news is the price that have come down, which I have heard that bit of information. However, the base in renewable energy is extremely low in India, so you can have growth rates that are very large, but they're still from a really low base. So really, it's not in percent that this needs to increase, but it's actually in quantity. But yes, I do think that India can leapfrog, and I do think that it would be extremely helpful if the price went down and if the investments were massive in India, including from other countries if they so wish. On where needs to do the push, that is such an excellent question to end. I think it needs to come from you, and you, and you, and you. This is the people ask me a lot, what can I do, with the feeling in their eyes that they are hopeless. And I actually think that we are not hopeless. There is a lot that an individual can do, some of which I have shown here. But the biggest thing that individuals can do is use your sphere of influence. Everybody has a sphere of influence. You have your family, you have your friends, you have your boss, you have your environment. And if everybody who actually cares and wants things to happen in decarbonization use their sphere of influence, the movement would grow much, much bigger. That's what Christiana Figueres did, and that's the reason why we have the Paris Agreement on climate change. To move to the next step, we also need to do it again.
Thank you, Corinne. I think we should be grateful that we have people like Corinne to take these messages forward for us.